Before the break, I described to you the principles of the transition from the stage of pre-normal science to normal science. Pre-normal science has these different schools, different ideas, different viewpoints, and we have a transition then to a unified point of view, and that is developed through a victory of one of the schools. The victory of the schools is based on an extraordinary achievement, and the judgment that the achievement is extraordinary is based on scientific values. Okay? And the scientific values are those which are pretty plausible to all of you, namely scope, accuracy, predictive power, consistency, and fruitfulness. And I will give you now an example, and that's an example much nearer than this electricity research from the beginning of the 18th century. It's something happening in the beginning of the 20th century, namely it's the victory of Bohr's atomic model. Right? Bohr's atomic model is so-called planetary model, where I have a nucleus, a small nucleus, positively charged, and the electrons traveling around it in sort of circles. And in order to show you, this was in atomic theory really the first phase of normal science, and I tell you a little about it, which is of course then quite plausible because you are familiar with the fundamentals of atoms. A certain consensus that atoms exist was only reached in the end of the 19th century. Before, there were different viewpoints. You know, some people thought that atoms exist, other people did not believe in the existence of atoms. At the beginning of the 20th century, most people believed in the existence of atoms. They said, yes, matter is not continuous, completely continuous, but matter is corpuscular, right? There are somehow small particles like the Greek atoms. The atoms is an invention by the Greeks. It's something which you cannot divide. That's the literal translation of atoms, something which cannot be divided. And the basic idea was, yes, matter has a corpuscular structure. There is something like atoms, you know, units, small units, and all matter is composed of these small units. The question is, what is the nature of these small units, right? What is it? What people knew in the beginning of the 20th century was that in these small units there are positive charges and negative charges, right? And that was a development, of course, having begun much earlier. It was a discovery in the 18th century that there are two sorts of electricity, right? Negative and positive. It was a very deep invention that gave an explosion of results, because once you order the electric phenomena by means of positive and negative charges, which is a completely new idea, then you get a very powerful theory, and it's so powerful that still today, of course, we believe in electricity that there are positive and negative charges. It's part of the most fundamental models in physics. The Standard Model, of course, works with positive and negative charges, electricity. Okay, so it was known that there are negative and positive charges somehow in the atom, but people didn't know what the structure of the atom was. And one very popular idea of the atom was that the atom is some sort like a cake, right? A continuous cake that is positively charged, and in that cake, like raisins, there are small pieces of negative charge, right, in between, right? The whole thing is neutral then, if that has, say, the cake stuff, the continuous positive charge, say, is 4, and then these little spots have then a charge 1, -1, then the whole thing is neutral. And that was the basic idea, that somehow that's a unit, some sort of sphere, you know, positively charged, and in between are these little spots like raisins in a cake. Therefore, it was also called the raisin cake model of the atom, where these negative charges. Now there was a guy in England, in Britain, Rutherford, Ernest Rutherford, and you may have heard his name, who was a very famous experimentalist. And what he could show is that this model is false. That doesn't really work. And what he did is he sent electrons to the atoms, and what he found is that most of the time the electrons go through the atom, and in some exceptional cases, which were extremely surprising, the electrons came back. right? And that is that somehow the structure of the atom must be different. It must be such that the atom itself there is something in the center that's positively charged, and then there is much empty space, and somewhere there must be something negative, but he didn't know how, from the experiments. He said mostly an atom is empty space, which was a real big surprise. But in the center, somehow there is a positive charge such that if an electron comes straight to the center, it's repelled and comes back. So people were quite surprised. Most of the electrons that were sent to some piece of, say, a sheet of gold or something, most of the electrons went straight through, but a few came back. They said that's very, very strange. So that were the empirical data that were known. People knew there were atoms. This was also the experience of chemistry that was strongly suggesting that there were discrete units. It was not just homogeneous and continuous. Matter was just somehow built up of atoms. But the problem was, what is the structure of the atom? The problem here is from electrodynamics that you know that this can't work in a sense. This model that in the center there is a positive charge and somehow around it are the negative charges. This can't work, this can't be true from the point of view of electrodynamics. Why? Because these charges go immediately to the center and the whole damn thing collapses, right? So there is no way that we have stability such that there is a vacuum, so to speak, within the atom. There is just no way. Why not? Well, because the negative charges are attracted to the positive charges, and the empty space here won't be stable. So matter will always collapse. And of course, it's one of the most fundamental aspects of matter that it is stable, that it does not collapse. So it was a big mystery by these experimental results that most space occupied by an atom is really empty space. It was completely incomprehensible how this empty space could survive in atoms. People didn't understand that at all. So here comes, in 1913, a young, completely unknown guy from Denmark. And Denmark was certainly not in Europe the center of theoretical physics. It was just a small country, and there were a few Danes sitting around, and a completely unknown guy named Niels Bohr. And Niels Bohr developed a model of the atom that had extremely surprising properties. It was not fully understood at that time, but the Bohr model of the atom was extremely surprising, such surprising in 1913 that people did not believe it in 1913 and not even in 1914. People did not believe it. They said, that's a sort of funny game, what he's doing, but it's not real physics. So they didn't really believe it. But what Bohr's model did, it was first a description of the positive and negative charges. So the Bohr model is the following, that it says, if you have an atom as a whole, then there is a very, very small core, a nucleus, and that is positively charged. That's in the center. And then there is much empty space, right, vacuum, and around this are circling the electrons, right? They are circling around here, around the nucleus. And there's a distance here, or this one here to this one here is 10 to 5, 10 to the 5. So if we have an atom, say, of size 1, then the center, the nucleus in the center of the atom is extremely small. It's just 10 to the minus 5. It's very small. So most of it is empty space. So people, of course, saying, well, that's not stable. Right? If you have electrons, if they sit here statically, they run immediately to the center. They are attracted to the center. And if they are cycling around here, that's not possible either, because electrodynamics then tells you an electron that's cycling loses energy, right? It radiates. An electron that has a curve radiates. That is a result of classical electrodynamics. So it loses energy. Losing energy means it becomes slower, and it's circling into the center. So the atom isn't stable. That was the first step. If you have a distribution of charges, distribution of positive and negative charges in that way, that you have a positively charged center and you have electrons trying to circle it, the immediate answer from classical physics is that won't work because the atom isn't stable. And as I said, one of the fundamental properties of matter is that it is stable. Right? It doesn't collapse within 10 to the minus 5 seconds. It is stable. It survives for years and decades and centuries and everything. So that was the first step, but that first step, of course, must be supplemented by something. Well, what Bohr postulated, and it was really a postulate that one did not really understand, and therefore it was also refuted by many people, he said, well, that doesn't happen. Doesn't happen. No. The orbits of the electrons are stable, period. Right? Please swallow that. That was the message. I don't understand it, but I can tell you my model of the atom is such that we have a positively charged center of the atom, and then we have stable orbits for the electrons. They can do that, and it's stable. Right? I know it's in contradiction to classical physics, but that's the postulates, and atoms just work that way, period. Right? People had to swallow that. That was part of it. Now, this has, of course, a wonderful consequence, and this is why Bohr had introduced it. You get the discrete emission spectra of atoms, and that's the following. You may know that if you have a gas in a container, right, and you heat the gas, then it starts to radiate, and the radiation that comes out, say it's light, and then you send the light to a prisma, and then you get the spectrum. And the spectrum is not a continuous spectrum, but you get emission lines, right? You get certain characteristic emission lines. That's called the discrete spectra. So if you have light from a gas, say, from hydrogen or whatever it is, and you analyze the light that comes out, that is generated through heating, you get discrete spectra, discrete wavelengths. So you've got lambda 1 here, and here different lambda 2, and here lambda 3. These discrete spectra were known, and they were very important in astronomy because you could identify the elements, right? You had a certain spectrum, and then you could say that spectrum belongs to a certain element. So the question was, say, if you've got H2 here, hydrogen, and you heat it, and you get an emission spectrum, the general idea was that from the structure of the atom, we must be able to understand in principle, first of all, why we have discrete emission spectra, right? That was the first step. And the second one was, why has hydrogen this spectrum and helium another spectrum and whatever element you take, again another spectrum, right? Not only that the spectrum is discontinuous, but also where exactly the lines were. And Bohr's model was the first model. As I said, the spectra, these regularities about the spectra were well known since the 1870s, 1860s, when people started spectroscopy, and it was a very important instrument in astronomy because then you could describe what elements were in the sun, for instance, right, and in the stars, which was an immense discovery in astronomy, that's spectroscopy. So one knew the rules, and also there were certain laws about spectra that were well known. And the general question was, well, if these spectra are generated by the atoms, then somehow we should be able to understand the spectra, the specific line spectra emitted by a certain element. We should be able to understand them in terms of the structure of the atom, right? That was the idea. And that was Bohr was able to do. Bohr said, look, I can really tell you how spectra work. That's the following. What we have is we have different sort of stable orbits of the electrons around the nucleus. There are different possibilities. Not everything is allowed. Only certain orbits are allowed. For instance, one here, and then one here, and another one round here, right? Not all orbits are allowed. Only a few orbits are allowed. Okay? He could describe that. And they said, you know, what a spectrum is, or what the emission of light is simply, you have an electron sitting here, in which it has more energy than in the inside, and then what the electron does, it jumps from one orbit to the other orbit. And that energy difference here, that delta energy, that's responsible exactly for one particular line that's here. Because that's exactly the energy difference that you need, and then the energy is translated into a certain wavelength. And because we have discrete transitions from here to here, for instance, from here to here, or from here to here, different transitions, and all these transitions generate a particular line. So what you get is you get immediately by this model, by having these different shells, right, different allowed orbits for the electrons, by this simple rule that not all orbits are allowed, you get immediately, qualitatively, the line spectra. And also, if you fill in the details, how big the charge is, how big that charge is, how the energies here are, then you could calculate, indeed, the spectra. And the point was that Bohr could calculate already in 1913 the spectrum of hydrogen. And that was an incredible success. Right? He was able, from his model, to use his model, apply the model to the hydrogen atom, using the mass here, using the mass of the core, the nucleus, using the mass of the electron, and using the charges here. And then he could derive from his model the line spectrum of hydrogen. Right? This was predictive power and accuracy. Right? The values that I mentioned here. Scope, accuracy, predictive power. The thing was not consistent. Right? Bohr's model is not consistent. But it is able to predict something that no one else could predict. All the other atomic models were completely unable to deduce the line spectrum qualitatively and also quantitatively to calculate the line spectrum of hydrogen. And that was an unbelievable success. It was said, but other people said, look, I value consistency very highly. And Bohr's model is not consistent. Why is it not consistent? It violates classical electrodynamics. It simply says, these orbits are stable. No explanation. Classical mechanics says, no, they're not stable. Right? Bohr says, yes, they are stable. Why did he say so? Well, he said, I know that matter is stable. Right? Somewhere the stability must come from. I don't understand the stability, so I postulate it. And he postulated the stability of the atom such that he got the line spectrum, right? That he got the correct line spectrum by saying, yes, not everything is stable in the atom, but only a few of these, right? It's very specific. And he gave a rule how to calculate them, but you didn't understand the rule, really. But you could calculate then the stable orbits, and from the stable orbits you could calculate the line spectra, and the line spectra for hydrogen were correct, right? So this is an example where all other people who studied atoms and had different ideas of atoms, they could never ever compete with Bohr's model because Bohr could calculate the line spectra. And the line spectra, as I said, were known for decades, that be measured with extreme accuracies, and were extremely important for astronomy and, of course, for chemistry. I mean, much of chemistry, chemical analysis even today is, of course, based on spectroscopy. You just heat the stuff and look at the spectrum, and then you know what it is, right? It's wonderful. It's very easy. Physical method to describe, to identify chemical elements and also compounds. So it was incredible what the model was able to do by calculating that. And then people said, look, this really solves some of our fundamental problems. It at least describes the stability of atoms. It doesn't really explain it, but stability of atoms is inbuilt in the model. And the stability of atoms, although we don't understand it really, therefore we are a little unhappy about it, we must accept because what this delivers, this assumption of the stability here, what it delivers is the fundamental stability plus the line spectra, the discrete emission spectra. And no one else could do that. No other atomic model could do that. And then people said, that's the way to go, right? That model solved some of our fundamental questions about what atoms are, right? It does solve them. And what you get is, of course, the feeling, that's what I described there, you get the feeling that some of the fundamental problems are really solved and that it opens avenues for further research. Once you know that this is the structure of the atom and you've calculated, say, for hydrogen the spectrum, of course the next step is to calculate the spectra for other atoms, for other sorts of atoms. So you had plenty of things to do. You could measure more spectra and then try to explain them on the basis of Bohr's model. So what you see, the fruitfulness for the future, not only for that particular case, hydrogen, but also the fruitfulness for further research. The scope, immense. Right? It's an immense scope when you know what an atom is, what the structure is. You can do many, many things, ask many, many questions, and answer many questions on the basis of this model. And that is what indeed happened then. It took 2 years, in fact, 1915, a very powerful physics group in Munich, around a famous theoretician, Arnold Sommerfeld. He started taking up the model And because he was a giant in the field, he was highly respected, and he was first convinced, well, this model is somehow right. And they started there then calculating things, and then in a very short while, everyone else in atomic physics accepted Bohr's model. They said, that's exactly the right way to go. So it took, from the invention of the model from 1913, it took something like 2 years. And before, there were some 10 years or 15 years, people thought about atomic models. They had different schools. It was pre-normal science, right? The cake model was one of them. This cake raisin model was one of them. And other models were around as well, ring models and complicated stuff. And that model came then in 1913 as one additional model. And then people realized, oh, that's much, much better than anything else, right? It's extraordinary. It's quite clear it solves the fundamental problems of the field. Of course, there are further questions. It doesn't say that's absolutely the end. We know everything now, because there was still this riddle about the stability of the orbits that one didn't understand really. But it was quite obvious that given the stability and its explanatory power for the spectra, that people thought there must be something in it, right? It must be somehow wrong, right. We don't fully understand it, but it must be somehow right. So they accepted the model. And as I said, Bohr's atomic model explains the stability of atoms. Well, I do scarce quotes here because it doesn't really explain them. It builds stability into them, but in a very specific way. It just doesn't say, oh, atoms are stable, period. But it says very specifically what the stability of atoms consists in, namely in the choice that certain of these orbits are allowed. And they are stable, although classical electrodynamics tells you they are unstable. But Bohr says by postulating, no. Here are some specific things that are stable. And that's, of course, then, it's a sort of explanation. It's not really an explanation, but it's not a simple postulate that you simply, without any sort of specificity, say, oh, yes, atoms are stable, period. I don't understand it, but they are simply stable. No, he says much more. He says there is a very specific stability, namely specific orbits are stable and allowed, and anything else is unstable, right? When an electron would be here, no stability at all. It can't stay there. Right? It does something and moves somewhere, and from here to here, it's an almost instantaneous process where the atom moves from here, and it's a very precise distance here that is reflected then in very sharp spectral lines as they were observed. Okay, so this is a concrete example, and I hope you could follow the physics here. I guess you must be able to follow the physics. Also, the water engineers have enough atomic model and so on. Yes. A little plausible? Okay, half plausible. Well, Google Bohr's atomic model, you can read more about it. It's a very, very interesting phase in the development of science. And I showed you that in order to illustrate what I mean when I say that the achievement that leads from pre-normal science to normal science may be such an extraordinary achievement based on these values here, scope accuracy and so on and so forth, by which you evaluate the model, in this case the Bohr model, and the evaluation is quite clear how you get the impression that this is the future way to go, and why this model is just very, very much better than any of the alternatives. And then if you worked, say, for 2 years on such a model, right, on the cake raisin model, that you say, I did not get anywhere. I don't understand the stability of this thing here, right? Because why do the electric charges, the negative ones, stay inside the cake? Why should they do that? I mean, there's repulsion. They move away. So what keeps them there? You don't understand anything. Is there any way that from this cake model you can go to can explain the line spectra, the discrete line spectra? You don't see any way, right? No way. But then you look at Bohr's model and say, wow, it's just much more powerful, right? It's a way from which I can be sure if I use that model, it does not only explain H2, hydrogen, but it may explain other features of the elements as well. You may understand different things. And what one sees immediately, if you study that a little, that you get a handle on the periodic system of chemical elements, right? This was periodic system of chemical elements was known since the 19th century. People know that was in the second half of the 19th century it was discovered, and people knew there was this structure, you know, that 92 elements have a certain sort of periodicity in the periodic system of elements, and you could immediately see that you have a potential here from the atomic model to explain that, because you've got these different sorts of orbitals, and different numbers of electrons can be in one of these orbitals, and that is immediately a link to the periodic system in chemistry, which is also, of course, to be explained by an atomic model. If you believe in atoms, and we have different sorts of atoms corresponding to the different elements, chemical elements, then of course the laws that govern the chemical elements must be somehow derivable from the atoms, right? And you saw immediately when you see this model, you see immediately the potential to do that. And that's, by the way, that Bohr discovered on the basis of his atomic model. He discovered new elements. In 1921, he gave the Nobel speech in Stockholm, and he described the discovery of a new element based on Bohr's model, because he could calculate it and then the chemist could find it. Right? So it was absolutely right that people then joining Bohr's model in 1915, that they saw correctly that it had great potential. And then between 1915 and, in fact, 1922, all the physicists working in atomic physics based their work on Bohr's atomic model. And this was a phase then of normal science. No competition between models. No competition between schools. Everyone knew that's the basis for physics. Atomic physics is built on Bohr's model, period. Right? No further discussion about that. And that is what we discuss further then in normal science. Once we have, by a triumph like this one of Bohr's model, as one of the schools in competition with each other, once one of these schools has won, right, then a new sort of practice emerges. Because you don't have to look at competing schools any longer. There is just one school. And that's not a school, that's just physics then, in that particular. That's just atomic physics. So after 1950, this was atomic physics. Period. Atomic physics was done on the basis of Bohr's model. And this is then normal science that I described, the transition to normal science. And here is then the very, very first and preliminary description of what normal science is. Namely, normal science is a scientific practice that is characterized by a consensus of its practitioners about the fundamentals of the field. Right? And that is to be illustrated here with Bohr's model, that the fundamentals of the field, namely atomic physics, that is the structure of the atom. Right? And everyone agreed. Right? And that was a fundament, a real fundament for atomic physics. And it lasted, well, in that case, only 7 years, but still it was extremely fruitful research. Up to 1922, Bohr's atomic model was completely unchallenged. Many, many problems worked, and I'll describe the practice of normal science a little later. And the point is simply that we have a consensus. That's the most important thing in comparison to this pre-normal phase where you have different schools. And you know, you may belong to one school, but you look at the other schools. Are they more successful than my school? Oh, I try to do here, but I'm not sure. It's a way of uncertainty, and that's just different from a science where you are sure you know what an atom is, right? And that was the case here with Bohr's model. Okay? So, more specifically, this consensus can be described by a number of points, and that will take me quite some time to develop that, but it's very important. This is this descriptive form of philosophy of science, as I announced it, that we now describe specifically this phase of normal science. That's the main and most important, well, most important is an exaggeration, but a very important phase. The pre-normal phase is something which you leave after a while. In the natural sciences, this has happened in every case. In the natural sciences, we are not in the pre-normal phase any longer. All of them are now in the normal or possibly in the revolutionary phase. And the really important one, the normal phase, that will also then give you the answers to the criticism of the deductive and the inductivism. We'll see that a little later. I do have some time left, a few minutes, I guess. Yes. Okay. Now, I'll give you 5 points of different length to characterize this practice of normal science. I told you, the difference between the phases is a difference of the practice of science. Right? Could be other differences, but it's a practice. The form of science, the way science is practiced, is different in normal science from the way science is practiced in pre-normal science, which is, of course, somehow obvious, because if you have you belong to a school and you know there are other schools, then of course you not only concentrate on your work in the school, but you have to observe the other schools as well, because it may be that the other schools make some progress and you don't make it, and you want to learn something from them or copy it or join their school or whatever. So you are constantly somehow, watching out what are the others doing, in the other schools. And you are constantly asking yourself, is my school really the right school? The others aren't idiots either, right? They have a different point of view, and you may understand the different point of view, but you may say, oh, is that right what they are doing? That's exactly, by the way, what you see today in the social sciences. Once you do social sciences, of course, you work mostly in a certain school, but you also observe the other ones, and you defend your school, and you defend the fundamentals of your school and other things, and all that doesn't happen if there's just only one school. Once you work within the Bohr tradition of the Bohr model, you don't defend the model any longer, you just apply it, right? But I'll give you more details about that. So I'm describing this practice of normal science, then by 5 different items of different length. It'll take me quite some time to describe that, because it's very interesting to see how paradigm theory describes this phase of normal science, and I think it's a very good description of real science. It's really a description how science works. If you look at different fields, and you will recognize quite a few things of your own research practice, I guess, when you look at paradigm theory. So the first, it'll be 5 items, and the first item I'm mentioning here is that the consensus about the fundamentals of the field provides scientists with a framework of research which they accept. This one here should go out. That's a mistake. All right, research, it's just one word. And again, this is very plausible, say, if you look at Bohr's model. If you accept Bohr's model as the model of the atom, you have a framework for your research. Of course, everything you say about atoms, you must articulate in terms of this model. Everything. Every experimental result about atoms, you must articulate in terms of this model, right? That's the framework. Once you do atomic physics, you refer to Bohr's model, and that's it. So it's quite obvious that once you have this transition to normal science, by the victory of one school, by having solved one of the fundamental problems, you get this fundamental framework, right? That's the solution of a fundamental problem. It tells you, Bohr is a solution to the fundamental question, what the hell are atoms, right? And Bohr says, atoms are like that, right? And then you have a framework, and then you work from this one, and you have a consensus, and everyone agrees with you. Every fellow physicist agrees with you about that. And that's a very different sort of workings, much more collaboration, much less competition, at least about these fundamentals of the field. All right, I think the next point is, yes, that leads me too far away, so we make the break here. So think about that, and the other things will be quite plausible. The other points that are following will be partly quite plausible, sometimes also surprising aspects of the practice of normal science due to the consensus, and I'll continue here next week. Yes, please?
I have one question. When you said that in astronomy there was not such a divergence, there was no free...
No. That was badly expressed. There was this, certainly. Yeah.
My question is, wasn't such a thing the idea when people did not know that the Earth was round before Galileo appeared, and they found the Earth was flat? I mean,
well, I'll come back to that next time, okay? That's false what you're saying.
okay.
It's absolutely false. Galileo did not discover that the Earth was round. That was known since 400 before Christ. Everyone knew it. It's false. No. I'll come back to it next time, okay? I start next lecture with that question. Okay, so have a nice, wonderful 7 days, and I'll see you next week.